All right, welcome to this explainer. Today, we're going on a seriously fascinating journey. We're going to completely deconstruct current electricity. We'll trace its path from this chaotic, microscopic dance of individual particles all the way up to the predictable macroscopic behaviors that literally power our modern world. So whether you're just refreshing your physics knowledge or you really want to know what actually happens when you flip a light switch, you are definitely in the right place. Let's get into it.
To make this dense, physical topic easy to digest, we've broken it down into 5 quick chapters. First, we'll define the flow of charge. Then we'll look at the obstacles it faces with resistance and Ohm's law. Next, we'll navigate complex circuits, figure out how we store and use power, and finally, we'll explore how scientists actually measure these invisible forces.
Okay, Chapter 1, the flow of charge. To really grasp electricity, we've got to start right at the foundation. What is it at its absolute most microscopic level?
Well, at its core, electric current is just the flow of electric charge over a specific amount of time. Mathematically, we define instantaneous current as I equals dq over dt. But here's a kind of fun fact for you. Even though current obviously flows in a specific direction through a wire, like from a battery to a bulb, it's technically classified in physics as a scalar quantity, not a vector. It's actually one of the 7 fundamental physical quantities, right alongside things like mass and length.
Now, I want to test your intuition here. How fast do electrons actually travel inside a copper wire the exact moment you flip a light switch? We intuitively feel like electricity is instantaneous, right? Like the second that switch is thrown, boom, the room is flooded with light. So those electrons must be zooming, right? Well, prepare to be surprised. The actual speed, which is known as the drift velocity, is roughly 0.1 millimeters per second. That is incredibly tiny. To put that in perspective, individual electrons are drifting through that copper wire literally slower than a snail moves across a sidewalk.
So, how on earth does the light turn on instantly? Well, it's not about a single electron sprinting all the way from the switch to the bulb. See, inside the conductor, electrons are already constantly bouncing around in random thermal motion at immense speeds. But the moment you apply a voltage, you create an electric field. And this field pushes the electrons, creating a massive chain reaction. So while the net drift of the individual electrons is crazy slow, that chain reaction, the actual signal itself, moves through the wire at nearly the speed of light. That brings us to section 2, resistance and Ohm's law. Because as you might guess, our electrons do not get a free ride. They face obstacles.
First things first, we need something to actually push the charge. You'll often hear the term electromotive force, or EMF, but actually, scratch that, it's a historical misnomer. It is not a physical force measured in newtons. It's really the total work done or the energy supplied by a cell, like a battery, to move a charge completely through a circuit. It acts just like a car engine pushing a vehicle onto a highway, fighting against the friction of the road. Now, what's super interesting is how different materials react to that push. For standard ohmic conductors, like copper and silver, they obey Ohm's law perfectly, meaning voltage is directly proportional to current. Simple enough, right? But then we have non-ohmic conductors, like the semiconductors inside your computer. For them, Ohm's law completely breaks down. In a normal piece of metal, heating it up increases its resistance. But in a semiconductor, heating it up actually frees up more electrons and decreases its resistance. It's completely backward. So when building circuits, engineers use these tiny components called resistors to control this flow. But how do you actually know their value just by looking at them? Well, to figure it out, generations of physics students have relied on this classic, kind of funny mnemonic device. B.B. Roy of Great Britain had a very good wife. Here's how it works. This sentence basically decodes the tiny colored bands painted on a resistor into exact mathematical values. The first B stands for black, which is 0. The next B is brown for 1. R is red for 2, and so on. So the first 2 colored bands give you your digits. The third band gives you the multiplier. And a final band at the end, which is usually gold or silver, just tells you the error tolerance level of that specific component. It's a brilliantly simple little system for a highly technical task. All right, moving on to Chapter 3, navigating complex circuits. Now that we have our individual components, how do they combine into complex networks? Think of it like a giant city traffic grid. The crucial point here is that in any complex traffic grid, cars can't just magically vanish into thin air, right? The exact same rule applies to electricity. Kirchhoff's current law, or KCL, acts as our junction rule. It strictly states that the total current entering any junction must absolutely equal the total current exiting it. This is totally rooted in the fundamental conservation of charge. Electrons simply don't disappear, and they don't pile up at a wire intersection either.
Then, to calculate the voltage around these complex loops, we use Kirchhoff's voltage law, which breaks down into 3 easy steps. First, you pick a closed loop in the circuit. Step 1, track the potential raise. That's the energy supplied by the battery. Step 2, track the potential drops, the energy burned off by the resistors. And step 3, you just set that entire sum equal to 0. Ultimately, this rule is really just a mathematical statement of the conservation of energy. Whatever energy goes into the loop must be 100% used up by the end of it. Which segues perfectly into Chapter 4, Storing and Using Power. We know energy goes into the circuit, but how exactly do these circuits store it for later, or burn it off to actually do work? For storage, we use things called capacitors. But here's the catch. A capacitor doesn't just charge up instantly. It actually follows this very specific exponential mathematical curve that's governed by its material, known as the time constant, or RC. So at 0 seconds, it's completely empty. But after exactly 1 time constant has passed, it will predictably charge to exactly 63% of its maximum capacity. Mathematically speaking, it requires an infinite amount of time to reach a true 100% full charge, though practically it gets close enough after just a few time constants.
But what about the energy that isn't stored? Remember those incredibly slow electrons drifting through the wire? Well, as they bounce and crash their way through the atomic structure of the metal, they physically hit positively charged ions. This microscopic friction causes vibrations, and those vibrations generate heat. The power dissipated as heat is calculated as I squared times R. And you know what? This is exactly why your high-power everyday devices, like your laptop charger or a hairdryer, get so incredibly warm to the touch. And this brilliantly illustrates our final chapter, measuring the invisible. We're dealing with invisible forces and microscopic collisions here. So how do we actually observe and measure these values without breaking the very system we're trying to study?
To do this, we use some incredibly clever external tools, usually built from a basic component called a galvanometer. To measure current, we create an ammeter but putting a very low resistance shunt in parallel. This safely bypasses most of the current right through the meter, without choking the circuit itself. On the flip side, to build a voltmeter, we add a very high resistance in series. This actually blocks the current from entering the meter, which allows it to simply measure the potential drop across 2 points without draining the system.
But I gotta say, the absolute true masterpiece of electrical measurement is the potentiometer. This device uses a long 10-meter wire and a zero-deflection galvanometer. By sliding a contact along that wire until the galvanometer reads exactly 0, it essentially balances the internal voltage against the wire's voltage drop. And because it draws absolutely 0 current at that perfect balance point, it can measure the true, pure EMF of a battery without altering the circuit in any way, shape, or form. It is just a stunning piece of clever engineering.
Which brings us to our final big takeaway. We've seen how energy is conserved, how it's transferred, and how it's lost. Now, in physics, the maximum power transfer theorem states that to get the absolute most power out of a battery, the external resistance must exactly equal the battery's internal resistance. But let me leave you with this somewhat provocative thought. If the internal and external resistance have to be perfectly equal to maximize power, that means exactly half of the energy is being wasted as heat inside the battery itself. Therefore, to achieve maximum power, you are permanently capped at a maximum of 50% efficiency. 100% electrical efficiency is quite literally physically impossible when you're pulling maximum power. It's just an inevitable, foundational trade-off of the electrical universe. Thank you so much for joining me on this explainer today. I really hope this journey from the microscopic electron to macro circuit design has sparked your curiosity to go out and learn even more.